All right. Well, thank you everyone for having me. I'm really happy to be presenting this. As Adrian mentioned, I am very newly a faculty member at Williams College. I'm a visiting assistant professor here as of the last 3 weeks. So up until that point, I was at the University of Vermont. And I've had the great privilege of working with a very collaborative team of researchers from colleges across the Northeastern United States, including Tufts University, Boston College, Bentley, and my former institution, University of Vermont. And this work has really centered on the North American Varve Chronology, which has really been a project for about 100 years, going back to the 1920s. So I'm going to dive a little bit into the history of that and how it was constructed way back in the 1920s, and then kind of revised mostly by Jack Ridge at Tufts University, and then how I've become involved in the last couple of years. So let me go ahead and just kind of orient you all with where we are, because I know folks are joining us from all over the world. So we're focusing in on the Laurentide ice sheet in North America. And this comes from a recent reconstruction by April Dalton that was just published last year. We've got a inner dotted line that shows kind of the minimum plausible extent of the ice sheet, this outer dashed line that shows the maximum extent, and then the white shows the most probable likely extent of the ice sheet. And where we're specifically focusing is on the northeastern United States, which was the southeastern sector of the Laurentide ice sheet. And I'm just going to zoom in on that area here. This is showing the ice sheet after it had pretty much fully retreated from this area around 13,500 years ago. And just want to orient you kind of with the place names here. So these are some of the kind of smaller states in the United States. We've got Vermont, which is my former home, Massachusetts, where I currently live. I'm currently located right around this northwestern corner. New Hampshire, Maine. This is the state of New York, the state of New Jersey. We don't really talk about New Jersey. No, I'm just kidding. But this is the region that we're focusing on today. And in general, this region is called New England. This is going to become more relevant as I discuss the history of this Varve chronology. But whenever I talk about New England, this is the area that I'm talking about, these states right here in the northeastern United States. Now, the Laurentide ice sheet really did a number on this region. The glacial geomorphology in here is just incredible. If you've never visited this area, it is absolutely gorgeous. We've got some big glacial cirques up in the mountains. We've got big U-shaped valleys. This one is in the Adirondack Mountains, Ausable Valley. We've got, here's another one in northern Vermont. This is Lake Willoughby. Big kettle ponds and other kind of ice contact features. This one is in southern Massachusetts on Cape Cod. Big striation features that are all over the place. And then, of course, we've got extensive glacial lacustrine sediment deposits in the low-lying valleys of the region. And a lot of these deposits have Varve features within them. So this kind of observation in the early days of European settlement in the area kind of led to the formation of the hypothesis that there used to be glacial lakes in this area. And what I'm showing here is a map of the biggest glacial lakes that have been mapped in the area. We've got Glacial Lake Hitchcock, which runs basically north to south, this long, skinny lake that also forms the modern Connecticut River. We've got Glacial Lake Merrimack, Glacial Lake Winooski, and over in New York, Glacial Lake Albany. And so the initial mapping and kind of exploration of these glacial lake features led to ultimately a 1920 expedition by De Geer, the pioneer of Varve chronologies, as well as Ernst Antevs, who was his PhD student at the time. And we were commenting on this photo at the very beginning before everyone got in. I just think that this photo is incredible to show kind of what the expedition clothing looked like in the 1920s. This is how they went out and took their cores and made their measurements and recorded Varve thicknesses. But Ernst Antevs did the majority of the fieldwork and almost single-handedly created a Varve chronology that stretched from nearly mid-Connecticut, which is here, all the way up around 380 kilometers to the northern edge of Vermont and New Hampshire up here. And here is what his Varve chronology basically looked like when he was done with it. So we've again got our glacial lakes in blue here in the same region, and all of these columns are sections of the Varve chronology. And we've got these lines showing where Varve sections from different lakes were correlated to each other based on matching Varve thicknesses. And so we basically extend all the way from Connecticut up into mid Vermont and New Hampshire up here. But then the problem was that there was this gap between the Varve sections in this lower part of the chronology and then these Varve sections in purple in the upper part of the chronology. And so to show that a little bit better, here's another way of looking at this Varve chronology. We've got all the different sections that were taken in different valleys around the region. So up in red here, these are the Varves that were taken from Hackensack Valley and the Hudson River Valley over in here. We've got the sections from the Merrimack Valley over in New Hampshire, and then this long set of sections from the Connecticut, Ashuelot, and Passumpsic Valley. Sorry, I always have trouble pronouncing that. And you can see that there's this gap in these sections. And again, it's located on the map right around here, and it was called the Claremont Gap. This was kind of the bane of Antev's existence in the 1920s when he published this chronology. He was not able to close this gap. And he assigned an arbitrary 248-year period to this gap and basically picked up his Varve count from the lower chronology back in the upper chronology with that 248 years just added on. But he didn't really have a solid constraint on that 248-year gap. So for about 100 years, we had this extensive lower New England Varve chronology that was unconnected to the upper New England Varve chronology up here. And that is pretty much where the Varve chronology was left for the majority of the 20th century. It was uncalibrated, so it was just floating in time. It was in Varve years with no connection directly to the calendar timescale, and it had this big 250-year gap right in the middle of it. The story then picks back up in the 1990s with the work of Jack Ridge at Tufts University. And Jack really set out initially to try to close the Claremont Gap. That was his initial goal with this research. So he went to this region in Claremont, New Hampshire, where the gap existed. And here's a zoom in of the area. It shows the Connecticut River Valley and some of the sites that were sampled by Antevs in these numbers and light dots right here. And Jack found two new areas. Here is Perry Hill in New Hampshire and Aldrich Brook in New Hampshire in the red lettering right here. And these were sections that Antevs missed, but Jack found. And he was able to extract Varve core segments from them, and through thickness matching was able to correlate these sites to each other. So in this graph right here, we've got the, this is in units of just Perry Hill Varve numbers, just arbitrary floating Varve years. In blue and red are the Perry Hill sites, and in green are the Aldrich sites. And as you can see, the correlation is pretty darn good between those sites. And then he was able to take those three sites, which straddle the Claremont Gap, and then connect them back to the overall Varve chronology that went the entire length of Glacial Lake Hitchcock, also the Connecticut River Valley. The names are used interchangeably. And you can see again this nice correlation that effectively closed this gap and made the record continuous. So at that point, by closing the Claremont Gap, Jack Ridge decided it was time for a new name. Whereas previously, Ernst Antev's Varve chronology had been called the New England Varve chronology, Jack realized, hey, we've got all these sections over here in New York, a region or a state that's not typically associated with the region of New England. And so we're going to call this the North American Varve chronology. I know that Alex Breckenridge is on this call, and you do Varves kind of in the Midwest part of America. And you might agree it's pretty presumptuous of Jack Ridge to say, hey, we're going to call this the North American Varve chronology. But people from the Northeastern US tend to think a lot of themselves anyway, me included. And so it's pretty fitting that we said this is now the North American Varve chronology. But putting that aside, this ended up being a really impressive piece of work by Jack Ridge. It recorded ice recession over nearly 6,000 Varve years and over 350 kilometers from south to north. And they're all connected. The central part of this follows Glacial Lake Hitchcock, this red segment here, but it's got accompanying sections from Glacial Lake Albany, Glacial Lake Merrimack, and Glacial Lake Winooski. And I'm just going to show you some snippets of this. So in this figure right here, it's a time distance diagram. And basically on the x-axis, we've got distance north from basically the bottom of this record right here. And as we move right in this panel, we're going to be going further and further north. And all of these lines are showing Varve sections. Where it's thin and blue, that are part of, those are Ernst Antev's original Varve sections. Where it's thicker blue, those were added by Jack Ridge in the 1990s. And where it's red, those were added in the 2000s. So those are kind of the most recent Varve sections. And so you can see that we have a really robust set of Varve sections that, along with the sections with the basal and ice proximal Varves, have a really good record of ice recession through time and the pacing of that. So as we go from Connecticut through Massachusetts, we have this steady ice recession here. As we move further north, and now we're in central Massachusetts, we have tons of Varve sections that together record this pattern of ice recession, including a re-advance and steady change in pace as we move further and further north. There are some gaps in the record, but for the most part, we have a really good idea of what ice was doing as it receded northward through New England. Here is the southern areas of New Hampshire and Vermont. This box is showing where this is. And again, we're just marching further north. Really good resolution up in this area, which includes a re-advance that is also associated with a set of moraines in this area. Further up in New Hampshire and Vermont, we just kind of keep plodding along. And then things get really interesting in northern New Hampshire and Vermont. So up here, we have a ton of records, really high density of Varve records that are all correlated to each other, showing this steady ice recession, and then what looks like a re-advance in far northern New England. And so this is kind of zoomed in down in this lower panel here. And this, the idea of a re-advance, which is based on three basal sections that all have pretty similar ages, but are located in like slightly apart from each other, is supported by an extensive set of moraines in this area that have been dated using other methods to around the same time as this purported re-advance. So this is great. You know, we have this interconnected Varve chronology that extends for over 330 kilometers, encompasses nearly 6,000 years of ice recession just in the Connecticut River Valley alone, but it's just floating. So the other thing that Jack did, and this is all published in his 2012 paper in the American Journal of Science, is he calibrated this to the calendar timescale. And so he did this using 56 radiocarbon ages on macrofossils that were embedded in Varves throughout the chronology. And this is just right here showing a simple scatter plot of where all these samples were taken in terms of the Varve chronology and what they were dated at in terms of their radiocarbon year, or sorry, radiocarbon age. Note that this is just simple radiocarbon ages. This hasn't been calibrated to the calendar timescale, but you can see a pretty darn good correlation between our Varve years and our radiocarbon ages. Obviously, there is some scatter. There's probably always going to be some, given the fact that not all plants die and are immediately buried in Varves. There's always going to be some delay. But overall, really good correlation. They then basically played a game of what is the offset between our radiocarbon years and our Varve years that gives us the best match to this data. And by that, what I mean is, you know, what year was Varve year 0? Was Varve year 0 18,000 years before present or 23,000 years before present? And they tried all these different possible offset matches. That's what all these lines are showing. These are kind of thousands of years. And they found that the best match to the Varve chronology based on the radiocarbon dates was an offset of 20,820 years. That's basically the calendar age of the Varve chronology year 0. So they have a fully interconnected 6,000 year sequence. It is now calibrated to the calendar time scale. And so this is now today what the North American Varve chronology looks like. So now in this time distance diagram, we're showing distance north of basically this point here at the bottom of this Varve chronology, that's Glastonbury, Connecticut. As we move to the right in this graph, we are moving further north along the Varve chronology. And on the y-axis, we have timescale in both Varve chronology years and calibrated timescale for the Varve chronology. This is a figure from 2012, so it uses the IntCal 09 calibration. That's, of course, now been updated to IntCal 20. But I have actually done the recalibration, and it only slightly shifts this graph. So overall, the timing of all these events doesn't really change too much with that new calibration. And so this tells a really interesting story about how ice receded in the Northeast. We have, starting around 18 to 18,500 years ago, ice recession, at least in Connecticut by that time, and it's at a pace around 50 to 100 meters per year. Things slow down a bit during the period between around 18,000 and 16,000 years ago. This is a period that is called various names. I know it as the older Dryas period, but it was a cold interval in the northeastern United States, so it makes sense that ice recession was slower during this period than before. Ice recession started to speed up a little bit from 16 to 15,000 years ago, and then rapidly accelerated during the onset of the Bowling-Allerud warm interval. In New England, this was an extremely warm period. It may have risen by as much as 10 degrees Celsius during this time period, after around 14,500 years ago. And we see that in the ice recession, which speeds up to almost 300 meters per year at this time. We had a brief cold snap around 14,000 years ago that separated the Bowling and the Allerud warm periods. And that was associated with this extensive set of moraines in northern New Hampshire and Vermont, which is also recorded in the Varve chronology. Another way of looking at this is just by plotting ice positions or ice margin positions on a map. That's what all these lines are, and the numbers show the date in thousands of years ago. These figures are available in Jack's 2012 publication. I'm happy to share that with everyone. You can take your time looking at all of them, but I just want to show kind of the status of the North American Varve chronology after Jack was finished working with it. And it's a pretty impressive piece of work. But now I'm going to transition to where I have kind of stepped in and started working with Jack on things associated with both varves and cosmogenic nuclides. And so I'm going to do a real quick overview of cosmogenic nuclides for folks who may not be familiar. And if you are familiar, feel free to just zone out for a minute and then tune back in. But I just want to make sure we're all on the same page when we're talking about cosmogenic nuclides and how they're used for deglacial chronologies. So this is an isotope system, and the origins of cosmogenic nuclides are cosmic rays. They're from supernovas, and they're mostly highly charged or high energy positively charged particles, mostly protons. So that's why they're called cosmogenic nuclides, because they have a cosmic source. And so in this diagram right here, we've got this positively charged high energy proton that's coming from space, and it hits an atmospheric atom and literally rips it apart. The reactions are called spallation reactions, but essentially it is ripping this atom apart and sending down a cascade of secondary particles, other protons, neutrons, little remnant atoms like this beryllium or maybe nitrogen. And this is the origin of some radioactive atoms in the atmosphere like carbon-14, is this cosmic bombardment by high energy particles. But this cascade of secondary particles will eventually reach the surface of the Earth and cause more of these reactions within solid rock, within minerals. Those reactions occur in the mineral, and they form these funky isotopes that basically aren't formed through any other process. And those are what we call in situ cosmogenic nuclides. The one that I use a lot is beryllium-10, but there's many others, including helium-3, aluminum-26, chlorine-36. But we're going to focus on this beryllium-10. Now, the reason that I'm bringing any of this up, the reason that it's useful for deglacial chronologies, is because you can use the accumulation of those cosmogenic nuclides in surface minerals to date the timing of ice recession. And here's how that works. If you have a landscape where you've got a glacier or an ice sheet, anything that's currently under the ice sheet is actually blocked from that bombardment of cosmic rays and secondary particles. So beryllium-10 doesn't form in any rock that's under the surface there. But any rock that's currently exposed, well, it is subject to that bombardment, and it is going to be forming these beryllium-10 or other cosmogenic nuclides over time. And so what that means is that if you sample a rock from outside the margin of the ice and you measure its current concentration, and then you take the very important step of predicting how quickly that beryllium-10 is being produced through time, you can backtrack out the initial age of exposure. This has ended up being a very powerful tool for constraining deglacial chronologies because you don't need organic matter. So you don't run into the potential problem of organic delay after deglaciation. Theoretically, you can date the moment that ice recedes off of a surface. Of course, it is much more complicated than that. That's mostly the theory, but it actually has been a proven method over and over again for constraining the timing of deglaciation in the absence of organic matter. Now, the step that I mentioned that's critically important here is that in order to accurately calculate an exposure age, you need to understand and predict how quickly that beryllium-10 is being produced through time. That's called the production rate. And that turns out to be the hardest component of calculating deglacial chronologies using cosmogenic nuclides, is accurately knowing the production rate at the sample site. Because the production rate of cosmogenic nuclides varies across the world. It varies with latitude, it varies with altitude. Here's just one diagram showing this. This is from Tibor Dunai's 2010 book, and it just shows with different latitudes from 0 to 60 degrees geomagnetic latitude, what the flux of neutrons is at that latitude. Remember, those neutrons are what are forming our cosmogenic nuclides. So essentially, the more neutrons that you have, the higher production rate of cosmogenic nuclides you have. At higher latitudes, you have higher production rates, and at lower latitudes, you have lower production rates. What this means is that you need to actually figure out at your sample site what the exact production rate of cosmogenic nuclides are in order to calculate exposure ages. This is often done by finding sites around the world where there are independent age constraints on certain events, maybe deglaciation, maybe a volcanic eruption, maybe deposition of an organic layer or sediment layer in a lake. And if you know the independent age of that event, you can measure the cosmogenic nuclide concentrations and back out the production rate. And so this is a map showing places around the world where this has been done. And you'll notice that one of those places, this dot right here, is right in the northeastern United States. And so let's dovetail this all back into our Varve talk, all right? So I bring all this up because the North American Varve Chronology, once it was fully calibrated and confidently set into the calendar timescale, was then used as an independent age control to calculate a local cosmogenic nuclide production rate in northeastern North America. So this was done by Greg Balco with help, of course, from Jack Ridge. And basically what he did was went to some of these sites in the northeastern US. So here's our map again of the region. All the places in triangles are places that he took cosmogenic exposure ages or cosmogenic measurements. And he compared them, the concentrations that he got, to the ages implied by the nearby Varve chronology. So here's a zoom in. We're basically in this region of northern Massachusetts and southern New Hampshire and Vermont, right around here. And going up the Connecticut River Valley, we have all these sites where Varves were taken, Varve sections were taken. In black are the Varves that are, or sorry, in white are the Varves that are ice proximal Varves, and in black are other Varve sections. All of them are correlated to the North American Varve chronology, and so they have a robust age constraint based on that calibration. That's what's shown here. We've got Varve years, and then in parentheses, the date and thousands of years ago. So Greg went out and measured cosmogenic nuclides in samples right next to the Connecticut River Valley, where we have robust constraints on the age of deglaciation. And from the measurements he took in those samples, basically said, this is the age of deglaciation, this is my concentration, I'm going to back out what the production rate through time was based on that. And this was a very, very successful project that he did. He was able to show that the production rate he calculated in New England was much better for constraining ages of deglaciation than the existing production rate that had been used in that region before. That's what this graph shows here. We've got another time distance diagram. Our 0 mark here is now this triangle right here, the Buzzards Bay Moraine in basically southern Connecticut and Massachusetts. And we're going northward following this dotted line as we move right on that graph. And what you see in this are, first of all these little triangles are radiocarbon ages that were used to calibrate the Varve chronology, and the line itself is the Varve chronology. All right, so deglaciation age, according to the Varve chronology, is shown with this line and triangles. And these dots are cosmogenic exposure ages. And where the exposure ages are kind of gray, this was using the prior production rate that was used in this region, and black is using the new calibrated production rate from this project. So you can see, especially in northern New England, up on these sites on the right, you can see all those ages shifting down and aligning perfectly with the Varve chronology. That was the whole point of this project, was to make them align with that Varve chronology. It didn't work in all places. You know, down in southern New England, we seem to actually have more of a mismatch from the old ages with the new production rate. But overall, the alignment with the Varve chronology was seen as being a success, and we basically now think that this production rate is more accurate for this region compared to the prior estimations. But if you're eagle-eyed and you're looking at this graph, you'll notice something. Down in southern New England, the mismatches become pretty big between cosmogenic exposure ages and radiocarbon ages. So these triangles are radiocarbon ages from the Varve chronology, but this black triangle is a core bottom radiocarbon age not connected to the Varve chronology, but it is considered a constraint on deglaciation. That is a little confusing, but essentially it is just another line of evidence saying when the ice sheet left that region. And as you can see, under this new calibrated production rate, our cosmogenic ages are saying that deglaciation occurred 2,000 years before the radiocarbon age says that it happened. And so this mismatch here, which was first spotted in around 2009 with this production rate calibration data set, and was kind of debated over for the last decade in the northeastern deglacial community, became kind of a sticking point between people who are radiocarbon deglacial advocates and people who are cosmogenic deglacial advocates. And caught kind of somewhere in the middle of those two camps were Jack Ridge and his Varve chronology, because the Varve chronology doesn't go this far south. The North American Varve chronology ends midway through Connecticut. And so there's about another 75 kilometers from the beginning of that Varve chronology to the terminal moraine that there's no Varve constraint. And the cosmogenic and the radiocarbon ages thoroughly disagree by thousands of years on the date of that ice recession. And so that is where my project really kicked in. So as Adrian mentioned, this was recently published in the Journal of Quaternary Science. And essentially what I did, along with my former doctoral advisor, as well as Jack Ridge from Tufts and other collaborators from Boston College and Bentley, is collected all of the constraints that we have on deglaciation, the timing of it in New England, and try to assess if we can figure out which one is most accurately constraining ice retreat and the timing of it. And the way we did that was by using the calibrated Varve chronology or sorry, not calibrated, using the Varve chronology as just a record of the pacing of ice retreat, and then reconstructing ice retreat according to all these different chronometers and seeing which one matched the pacing of ice retreat best to the Varve chronology. So I'll explain that a little more as I go. But this is kind of the map that we came up with. It's in New England still, and we've got in yellow the Varve chronology from Jack Ridge, the North American Varve chronology. Down here is another little secondary Varve chronology that was published in 2020, but unconnected to the North American Varve chronology. In diamonds, we've got radiocarbon ages from macrofossils at the bottom of lake beds, which are considered minimum limiting constraints on deglaciation. We've got in the circles radiocarbon ages on bulk sediment. And in green or pink squares, we've got cosmogenic exposure ages. As part of this project, we also calculated all of these middle New England exposure ages just to fill in the gaps that we had. And we basically said, let's find the timing of ice recession according to these different lines of evidence and compare them. And so that's what we did. So in this figure, by the way, this big blank right here, originally this map was an inset to this figure, but I wanted to blow it up so you could all kind of make out the details. That's why there's this big gap right here. But we took these lines where April Dalton kind of modeled the ice margin, and along those lines, we said, what do each of these chronometers say the timing of ice recession is? And that's what's shown in this figure here. So each box here corresponds to one of these lines, and they go from south to north. And so what you can see from this pretty immediately is that really far south, along the last glacial maximum line down here, we've got a huge disagreement between cosmogenic exposure ages and either radiocarbon method. We have cosmogenic ages saying deglaciation is probably between like 25 and 30,000 years ago from the last glacial maximum terminal moraine. Radiocarbon ages are saying no, that's more around 17 to 15,000 years ago, and Varves are somewhere in the middle. Again, this is this new Varve chronology from New York City and New Jersey that's unconnected to the North American Varve chronology. Sorry, I'm just noticing there's a alert. I'm just making sure, is anyone trying to say anything in the chat? Okay, perfect. Sorry, I just wanted to check on that, make sure I wasn't muted or anything like that. And as we move further north, what you start to notice is that those ages start to align more and more the further north you go. By the way, the cosmogenic exposure ages here are not calculated using the Northeastern North America production data set because those were calibrated using the Varve chronology. We use the global data set to try to avoid any problems of circularity here. And so you actually have this alignment of ages as you go further north. You know, as you get to these lines that are in northern New England and New Hampshire and Vermont, you start to have your cosmogenic and radiocarbon ages get closer and closer until they are practically right on top of each other, showing really good agreement. So this was the first observation that we made. We said, hey, when we collect all this data and we line up these ages together, we see this pattern of severe disagreement down south with narrowing disagreement as we go further north until our ages looked pretty much identical in northern New England. So to try to figure out what is going on, we used some Bayesian modeling to basically take the data from our cosmogenic ages, which are in pink, our macrofossil radiocarbon ages in blue, and our bulk sediment radiocarbon ages in yellow, and model ice recession according to each of them in a Bayesian framework. Then we compare them against the Varve chronologies. These are these black little spidery things, and see what patterns look the most similar, and if we can figure out why we have such a big disagreement in ages down south. So first of all, you can see again this massive disagreement between ages of cosmogenic and radiocarbon suggesting deglaciation. And you can start to observe a few things when you look at this modeling. You can see, first of all, that in kind of south and central New England, which is this area of the graph down here, we have the pattern of ice recession matching more closely between Varves and cosmogenic nuclides. And that's not even looking at the dates, that's just looking at the pattern and pacing. it looks like the pacing of ice recession according to cosmogenic nuclides is very similar to that implied by Varves. The cosmogenic nuclide modeling doesn't capture all the variability in pacing that Varves do, but overall the pattern is similar. When we get up to northern New England, though, it's almost the reverse. We have the pattern of ice recession according to Varves, this black line, matching very closely to the pattern indicated by either of our radiocarbon techniques. And so this is really interesting. We have cosmogenic nuclides capturing the pacing of ice recession most accurately down south, and radiocarbon capturing it most accurately up north. We spent a long time in conversation, our whole team, including Jack Ridge and Paul Bierman and others from around the northeastern US, trying to figure out what was causing this disparity. And we think we have an answer, or at least a hypothesis. Our hypothesis is that in the southernmost area of our study site, it's actually neither cosmogenic or radiocarbon ages that are accurately capturing the date of ice recession. We think that the cosmogenic ages are biased too old because glacial erosion wasn't that deep down south. And so we think that with that lack of erosion, we have some cosmogenic nuclides inherited from previous glacial cycles left over and kind of artificially inflating that exposure age. The radiocarbon ages we think are too young because we think that the early deglacial period was so cold and the periglacial conditions dominated that we actually had a significant delay in organic matter deposition, and therefore these ages are truly minimum constraints and are probably a couple thousand years too young. We were not able to narrow down our timing of initial deglaciation to less than a 4,000-year window between 20 and 24,000 years ago. That's when we think deglaciation first occurred. But then as we start to get further north, we think that glacial erosion deepened and therefore cosmogenic ages became more accurate and closely aligned with the Varve chronology. And we think as we approach the northernmost northernmost New England, we started having the deglacial conditions warm up, and the lag between organic matter deposition and deglaciation became less and less until it was more closely tracking deglaciation in those radiocarbon ages. We think our modeling might be a little biased by our old ages down south, and that's why our pattern of cosmogenic ages don't line up further north. But the fact that the ages all line up exactly when you just look at individual sites suggests that once we got around 400 kilometers north of the terminal moraine, either radiocarbon or cosmogenic ages were accurately recording ice recession. But further south, we don't think that's the case. And so that leads us finally into some future work that I'm currently doing with Jack Ridge. We want to test this hypothesis. And most of what we want to test is whether there is what's called cosmogenic nuclide inheritance in samples from further south. And we're going to do that by going to sites that Jack has previously visited, where we have these extensive sediment deposits from ice contact histories, and essentially sample some of the furthest down ice contact sediments we can find that were pretty quickly then buried by overlying sediments. And because they were buried and cut off from that cosmogenic cascade, whatever cosmogenic concentration we measure in those sediments should reflect the inherited concentration of sediment coming off the ice sheet or underneath the ice sheet at the time of deposition. So that's where we are now. I'm going to end it there, and I believe I have some time for some questions. So thank you very, very much.